And we said that in most cases that we're going to deal with in the class with an open system. So we have mass coming in and mass leaving. We're going to say that the time rate of change and velocity of the mass coming in is 0. The center of mass, right? So if I have a control volume, remember this is my system. Right here is my system. And I have mass, heat, and heat coming in, and mass and heat leaving. The system can also do work, so you can have energy transfer. But for mass coming in, there's a control volume of what's coming in, right? So this defines the control volume of air coming into my system, right? It's traveling at a velocity. There's a given density. There's a given temperature of this. And then, of course, there's a control surface and there's a boundary, right, associated with my control volume of mass coming in, but it comes into my system which crosses some boundary. So when I look at, this one's messy, so let's just look at the rate of all forms of energy out, okay? So there's the rate of energy out, has 3 components: heat, work, and mass. So there's a heat flux up, right? There's a rate of heat loss. There's a rate of power output, or not a rate of power output. There's a power output, or there's a rate of work done, or work out. And then there's the rate at which energy due to mass comes in. And so under these main assumptions, we said the velocity was 0, or v dot is 0. We said that, all we said, we just broke it down to a mass transfer rate in. So it simplifies to this. So the height, time derivative of the height of the output isn't changing in time. The temperature of I don't have that picture up, so the mass coming in, right, the control volume, the temperature within that control volume of mass coming into my system isn't changing in time. The pressure within isn't changing in time. So all I have to look at is the velocity and the mass flow rate and its average thermodynamic temperature, thermodynamic pressure, density, or specific inverse of that, specific volume. We went over this problem here. And this with the nozzle, right? Steam entering through a nozzle. And then so I illustrated this pancake, which represents the control volume for my gas entering, crosses my boundary into my nozzle. I have mass leaving. Now I have the same volume of my control volume in and out. The shape changed because it was a nozzle. And so this volume equals that volume, it just has a slightly different shape. Of course, I could make my control volume a part of this, make a control volume of the control volume, but nevertheless, this is the simplest way to look at it. So we went through this problem. So we did conservation of mass to get the mass flow rate as m dot. And then we can do conservation of energy, first law, right? Write out the first energy balance in rate form to solve for the velocity. We got an expression for the velocity. So, energy system, what does that represent? Question. Can't do it all. So what is the energy of my system? Energy of my system. What is the energy of my system?
Constant. The constant is inside, like you want inside the boundary.
Inside this boundary.
Yes.
That's why I want to get you guys to remember that. Energy of the system is all the forms of energy within this boundary. Okay. So when we do this rate form of the first law, this is energy in dot. This represents what? The rate of
The rate of energy is coming in.
rate of all forms of energy entering my system. This represents the rate of all forms of energy exiting my system. This is the rate of change of, the time derivative of the change in energy within my system. So, all forms of energy crossing the boundary, all forms of energy inside my boundary. Later on, we're going to do a second law entropy balance type form, and it's going to follow the same format where on the left-hand side, this represents all the forms of energy crossing my boundary, and this is all the forms of energy within. So if I plot the energies of my system, my nozzle, all the forms of energy within my boundary of my nozzle, as a function of time, it's not changing. Now, after I turn off the gas coming in and all this other stuff, right? Or I close one of the exit or something like this, this can change. But we're working at steady state, so then there's a delta E associated with this. But anyways, the slope is going to be, there is no slope of this line. So I get that. Yes?
So, since the change in energy is the energy of the system, we assume the system, whenever there is no change, has zero energy?
No. It has an energy. Inside my system, I have energy within it. I have mass within it. Right? There's a constant, over time, the total mass within my nozzle hasn't changed. Right? The temperature within my nozzle hasn't changed. The pressure within my nozzle hasn't changed. On average, right? Of course, there's a pressure distribution, but if I look at the average pressure and average temperature within, it hasn't changed in time. Now, if I turn off the gas coming in, right, then this may or may not change. Okay? But if I'm putting hot gas in and then it's even hotter or cooler gas out, and I turn it off, that means that hot gas is actually heating up my system. So if I were to turn off that gas, just from an energy standpoint inside, then I no longer have hot gas coming in. So my energy in my system is going to decrease after I turn off the input to the nozzle. So like if I have an aircraft engine and it's sitting there and it isn't on, and I have wind blowing, right? I have my big turbine on the jet engine. There's wind blowing, and some wind is going through. So if I look out on the wing of the aircraft and I have the engine sitting there and the wind's blowing, there's some wind coming through my engine. I could draw a boundary around it, and it turns out in that case, given that everything's at equilibrium, the wind coming in is going to be at the same temperature as the wind leaving. There's going to be, and say the wind velocity is constant, I'm going to have a mass flow rate of wind coming in and mass flow rate of air leaving. And I could plot, so given I drew a boundary around that, I could integrate all the forms of energy within and get the energy within my turbine sitting on my wing. Now I turn on my engine, okay? So I have fuel coming in, okay, so let's not talk about the fuel coming in and all that other stuff. Let's just look at the mass flow rate of air coming through, right? So now I have cooler air getting sucked in and warmer air getting sucked out. But the engine's not 100% efficient, so it's heating up. So it's getting hot. So if right here, if I were to change this and kind of just draw a diagram of what happens. So right here is where I turn on my engine, right? It does something like this. And then as it's idling, you have an idle, right? So then as it's sitting on the tarmac or whatever, you're going to have some steady state operation. And so now, over some steady state operation where it's just sitting there, and the rate of heat leaving is a constant, and the rate of air coming in is a constant, it's not changing in time. Then you get takeoff, and then you have something like that, right? But then you get to 10,000 feet, and again it's stable, and then you have landing. But there's steady state regimes within. But this represents all the forms of energy within. So in terms of that engine on the wing, we have a bunch of metal, we have a bunch of gas, we have a bunch of fuel, right? If we knew all the components and we had thermodynamic tables for everything we could look up and calculate based off the total mass what the total energy is. Does that help? That
Yes.
and then we finished up on here, and so we'll continue with this. So we had this very general introduction to thermodynamics example of a stator which increases the kinetic energy of a gas, and it does this adiabatically, which isn't very realistic, but because there is some heat loss, but the engineers design it in such a way so it's minimized, Q dot. And so we did this, and we first things first, we drew a schematic, and then we write out full energy balance, then we do this. So we have full energy balance, we have the rate of heat in, the rate of work in, or the power in, and we have the rate of energy due to mass in this case it's a gas, and then we have likewise on the output. Now in this type of problem, there is no work in and then there is no power out. There's no power in and no power out, or there's no W dot in and no W dot out. So this cancels out, that cancels out, that cancels out. It's adiabatic, so this Q dot 0. And this thing isn't changing height relative to sea level or rotating in any way, right? It's not rotating in some way, going like this or like that. So I can get rid of my Z1, Z2, and I can simplify it down to an expression like that. And then the question was, what is the velocity at the output? So I can simplify this in terms of V2, and I have a V2 squared there. So I get an expression like such. So next thing I wanted to do is I wanted to point out that sometimes we might not need to look up what the enthalpy is. So H1 is the enthalpy of what? H1 represents what? The enthalpy of the gas coming in, right? So if it's air coming in, I can look up, I get temperature and pressure of the air coming in, and I can look this up. Well, sometimes we can get around looking up these values, both of them, in some table, and instead the enthalpy is related to the heat capacity at constant pressure. So the heat capacity at constant pressure is the partial derivative of the enthalpy with respect to temperature at constant pressure. So the enthalpy is a function of temperature and pressure, but the partial derivative just is concerned with the change in one of the variables, so I keep pressure constant. Question?
Wouldn't your m dots go away because you're multiplying by 2 over m dot?
Yeah, they might. Probably.
Yeah, ends up just being 2 times H1 minus 2 times H2 plus V1.
Yeah. So it's like that. Yeah. Thank you. So I have this expression for the heat capacity at constant pressure. So I can redo this. And so I have partial H equals Cp dt, or delta H equals Cp T2 minus T1. And this would be the average heat capacity. So taking this type of approach, we can now plug in H1 minus H2 equals average T1 minus T2 into this expression, and so we get V2 equals V1 squared over 2 times 2 1/2. So H1 is the enthalpy at T1 for the gas. And H2 is the enthalpy at, I should put a comma here, P1 at T2, P2 of the gas. And it was at constant pressure, so P1 equals P2. So I can get an average enthalpy, right? By taking this plus this divided by 2. Same way I can get an average heat capacity. So if I plot the heat capacity as a function of temperature, and this would be T1 and T2. So I have two values here. So this plus this divided by 2 gives me something in the middle. Even if there's curvature to it, it's pretty close to right there. So analogous to this, I can just have my, I can plot H as a function of temperature. And it does something like that. And so T1, T2. I can get an average enthalpy between the two temperature ranges. This is the temperature of the gas at the outlet, this is the temperature of the gas at the inlet of my stator. Also related to this, what I did here is I just simplified it, but really it's the integral from T1 to T2, Cp of T, dt. So in this respect, my m dot H1 minus H2 is equal to m dot the integral from T1 to T2 Cp, which is a function of temperature, dt. And then it's approximately equal to m dot Cp average so if this temperature dependence doesn't have any funky curvature to it, right? It's pretty much a smooth line. I can approximate it as the value right there. I'm going to give you a little bit off, just like here. I can approximate it as the value right there. So if I were to get the total area underneath. Anyways, it's just, I just want to remind you that using this to get to this, just keep in mind that really you're doing an integral and you're just simplifying it by saying this has a very small or linear temperature dependence. Let's do a different problem. Let's do a heat exchanger. That's working at steady state. So given it's working at steady state, I have the rate of energy out is equal to 0. And in this heat exchanger, I have some rate of heat loss. and I have gas in, and it's going to be at 400 degrees C. And then through here I have a bunch of curvy lines and heat exchanging elements, but we'll just let it be a black box kind of inside, just a box to represent the system. We're not going to worry about how all the pipes. If I look at the radiator on my car, it's a heat exchanger. If I just, you can see all the small fins all over the place when you look at it, but let's forget about all that stuff inside and let's just treat it for thermodynamic purposes as whatever's there is there. All we care about is the average properties of the energy within. So I have gas out. And then we're taking gas in and gas out. And what we're going to do is we're going to use water in. And let's say it comes in at 15 degrees C and we get water out. And so we're going to have hot gas coming in and cooler gas out, and we're going to use water to cool the gas. So in here we have heat exchange between the gas and water, but we don't necessarily have to be that concerned with it. So we just drew a box around all this and then we defined our system. All we care about is the average energy within. Right? And given we're at steady state, we know that the change in all the forms of energy in isn't changing in time. So it's already out of the first law energy balance. Let's add a little complication to the water out. We'll say it's saturated vapor. So we have saturated vapor out at 2 megapascals. We can just say that, put any values in here. So we can say it's at 400, we'll just say that the gas in is at 1 atmosphere, or the gas, and the gas out is at 1 atmosphere. So we had very little pressure drop of the gas within, so we could just approximate it as atmospheric pressure. Of course, this is always, should always have a larger pressure than here, because we have friction at the walls of the tubing within. So there, because of that friction, you have to put in energy to get over that. Otherwise, all the fans that we would buy to circulate the air, we would just turn them on, let them spin, and then we would turn them off, and then the flow would just keep on going forever, right? So boundary, in the context of what we're talking about before, this is the same as a control surface. So, gas coming in, I told you the temperature and pressure of the gas in, I told you the temperature and pressure of the gas leaving. We also need to know what? So we'll just say the gas is air, so we have a chemical composition. But given the gas coming in, what do we also need to know? What's that?
You need to know the volume.
Okay, so you're saying know the inlet diameter of the pipe? We have to define a control volume. Okay, so that's where you said need to know the volume. But as soon as we say we define a control volume and we just say it's 1 centimeter cubed, right? So that defines the thickness of our pancake. Control volume pancake coming in. What do we need to know? We have gas coming in.
Velocity.
Okay, it's velocity. What's coupled to its velocity? We just had an expression. The mass flow rate. We need to know the mass flow rate of gas coming in. And because it's steady state, we know if the mass flow rate of gas coming in, we know that the mass is equal to the mass flow rate of gas leaving. So we have some m dot gas, right? And an m dot gas. Likewise, we have the same. We have some m dot water coming in. Now, it's liquid water coming in. And it's saturated vapor leaving. So let's just make a guess. What do you think the temperature of my water vapor leaving is? What's that? Above 100 C. Why do you say above 100 C? Okay, so what is the pressure associated with saturated vapor, right? In pascals at 1 atmosphere, what we're at right now. So 1 atmosphere is the same as 101 kilopascals, 101.3 something, right? Kilopascals. Now we have pressurized, it's pressurized. So as I pressurize a vapor, what happens to its saturation temperature? It goes up. So if you want to remember this, the quick way to remember it is to think about, well, I guess someone mentioned that on Mythbusters, they put somebody in an evacuated room and had a water bottle. They started decreasing the pressure and the water bottle started to boil. Okay, so one way to think about it, you go to Mount Everest, the top of Mount Everest, the water gets sucked out of you because you decrease the saturation temperature, right? It's lower pressure, so the water is like boiling out of you almost. It really evaporates easier. Or if with a pressure cooker, you pressurize it so you can cook at a temperature above the boiling point. So increase pressure. Now, of course, you can also draw the bell curve and you can figure this stuff out, right? So if I were to draw a bell curve, I can just do that here. And let's just say pressure, specific volume for water. As I progressively go up, I reach the critical temperature where you can't distinguish between water vapor and liquid water. That's really high, 600, right? Some degrees Kelvin for water. But each isobar is a higher temperature. Now I could change this to temperature here and specific volume, and then each one is an isobar at higher pressure. So there's a few days you can think of examples that are practical. Go to Mount Everest, or you're on a spacecraft that goes from Earth to Mars, and Mars has much lower vapor pressure, right? So you get out and suddenly your bottle of water boils and it goes off into the Mars atmosphere. But anyways, there's a bunch of ways to do it. So we know that this is going to be above 100 degrees C. Given them at 2 megapascals at 15 degrees C, we're in this compressed liquid regime over here. Okay, so let's just identify m dot gas is equal to, give them some numbers, 32 kilograms per second. I should have had minute, which equals 0.5333 kilograms per second. M dot H2O is equal to m dot gas divided by 15. So it's just some fraction. And I just made it this way because the mass flow rate of gas should be less than that of water, should be less than that of gas, because gas has less friction than water flowing through piping and stuff like that. But it is. So given I have that, m dot H2O is equal to 0.0355 kilograms per second. And then I have another, I'm going to just say I provided you some expression that Q dot, the rate of heat loss by my heat exchanger, is equal to 0.1 Q dot out gas. So my gas is coming in hot, right? I'm cooling it, and it's leaving cooler. So that means that heat is leaving my gas, right? So if I were to kind of look at it as, I'll move this down for the sake of analogy. So I have, this is my control volume of the gas coming in. And as it comes through all my piping and stuff like this, its temperature is decreasing. And so the temperature within here, there has to be heat loss out, and it's going to the water into the heat exchanger, and then it leaves at a lower temperature. And so there was some rate of heat loss from my gas passing through, and that is a percentage of the total heat out. So let's do full energy balance. We already identified that it's steady state operation. So let's write this out. So I have Q in dot plus work in dot plus m dot So I just kind of simplified. So this, I have all of gas. Instead of writing this whole thing out, I'll put a little bracket above it. But right here, everything here represents all the forms of energy associated with the gas. So when I look at my system, I have two forms of mass. I have two control volumes of mass entering, one that of that of gas and one of that of water. So when I do all my forms of energy crossing my boundary, I have to take into account, well, I should have put the bracket there, sorry. So I have my heat and work component, and then my gas component. So likewise, I have the same thing on the out, Q dot out, plus work dot out, plus energy out dot with the gas, plus the energy out dot of my water. In this case, it's steam, but I just use H2O. And of course, this I can write out as m dot H2O.
Can you move it down?
My velocity of the water coming in over 2 plus gravity times the height of the water nozzle coming in plus my enthalpy associated with the water. So I can take all this stuff, but before I do that, let's simplify and let's cross some stuff out in here. What is the heat in? What is my heat in?
0.
0. What is my heat out?
1 gas out.
Heat up, 1 gas out. Okay. My work in, or my power in. Yeah. So there's already been work been done by a pump to get the gas flowing through and the water flowing through. That's a different problem. We just drew our boundary around our heat exchanger. Now we could have some rate of power out as if, our radiator was vibrating, right? Then we would be doing boundary work. Our boundary would be changing in time and there'd be some power output associated with that. But the only way there would be net power out is if it was vibrating and increasing, nevertheless. But we have constant, our boundary isn't changing in time, right? It's constant. We're not considering thermal expansion. So across this, we have an expression for that. So we can simplify everything out. And we can get rid of these, right? So then when we simplify it, we got m dot gas H1 gas plus m dot H2O H1 H2O equals m dot gas H2 gas plus m dot H2O H2 H2O plus 0.1 Q dot gas. And so we know m dot, we can just say it's m dot gas. So m dot H2O equals m dot over 15. And we can simplify this further. So m dot H1 gas plus m dot H1 H2O over 15 equals m dot H2 gas plus m dot over 15 H2 H2O plus 0.1. So now we want, so to solve the problem, one thing we want to do is we want to kind of get an expression for how we can relate Q dot out of gas to Q dot in water. But Q dot out of gas does not equal this. We have some other term. I could look at it from a different perspective. Of Q dot H2 out, the minus sign, plus some other term. So the heat leaving the gas goes into the water, but some of this also gets radiated to the surroundings, right? Q out. So this other term here is Q dot out heat exchanger. Likewise, this term here is Q dot out heat exchanger. So I guess what I'm getting, so we can solve for this now we have two equations and two unknowns. But given I have this expression here, I can rewrite this as m dot H1 gas minus H2 gas, and then I can use my heat capacity relation. So m dot Cp average of my gas, T1 gas minus, and the same I can do here, m dot, but this time over 15, H1 H2O minus H2 H2O likewise m dot over 15 Cp average H2O T1 H2O minus T2 H2O. So I just wrote out a bunch of equations. I never really asked what you need to solve for. But in a lot of cases, I might have just asked you what was the temperature of the gas leaving my heat exchanger. So right here. So I might ask you to solve for the temperature of the gas leaving the heat exchanger. So you can kind of interpolate from a table and look it up, a table of H2, and solve for H2, or you can use the average heat capacity and get an expression for it. So I did this heat exchanger, and I did it from the context of this being a black box where we didn't have to care about all the tubing within. And I just drew my boundary around the outside. So I'm going to do a heat exchanger again, but this time I'm going to kind of just look at two of those instead of the whole heat exchanger as a whole, and all the winding of all the tubes and counterflow heating tubes within. Now I'm just going to say, I'm going to kind of do a transform on it, and I'm going to make all that winding into just this. So I have my water coming in this way and my gas leaving. So I have my water in, and I have water out. Right here, I have a little control volume associated with this. So instead of, I guess we could do gas, but I already made it for oil. So we'll just say that in this case, it's more of a car engine type an example, or not necessarily car engine, but we're cooling the oil with liquid water. So we have oil out. So of course I have water in, so there's a temperature associated with it, there's a pressure associated with it, there's a mass flow rate associated with it. Given that, we can get a velocity, right? And etc. And likewise, we can do the same thing here, right? And we can do the same here, right, for the oil and then oil. So let's just say the oil in comes in at 150 degrees C. it leaves at 40 degrees C. And the mass flow rate of oil is equal to 2 kilograms per second. And of course, m dot oil here is the same, 2 kilograms per second. So water comes in at a temperature of 22 degrees C, and the water leaving is unknown. The temperature of the water leaving is unknown. The mass flow rate of water is going to equal 1.5 kilograms per second. So of course the water out is going to have the same thing, right? Okay, to solve this problem, we're going to do it in 2 parts. So the last one, we just drew the boundary around everything, and we looked at all the forms of energy coming in and energy leaving, and we were given an expression which described the rate of heat loss coupled with some physics that took place within. In this case, we're going to look at this, but then now we're going to do energy balance on little things on control volumes within. So this part right here, I'm going to move down to here, and I'm going to make a box for my oil, okay? And here, I'm going to have a box for my H2O, and we're cooling the oil, right? So heat is leaving the oil and going into my water. And my oil is traveling at some velocity, right? But there's some mass flow rate associated with it. And because it's counterflow, my water has some velocity, but then there's some mass flow rate with it. So I just defined 2 control volumes, one for the oil and one for the water. I neglected the metal spacer between the 2. So I'll get back to this part now in a second. Above here, this is just some specific heat thing. So the first thing I want to do is I want to do energy balance for the oil. So I have energy in dot minus energy out dot equals the change in energy of my system, and my system is what? Remember, I took that other problem and now I'm looking at a small subset of it inside. And I'm doing energy balance from the oil's perspective. So my system is this. And then if I look at this, I have oil coming in and oil leaving. And then here, I have water coming in and water leaving. I have my system, which is a control volume of oil, and I have oil coming in and leaving it. So my system is an oil control volume. Is this a steady state problem? Yes? Okay, if it isn't, what can we say needs to happen for it not to be steady state? Let's assume it's not steady state, and let's pick something that we know is true for when it's not steady state, when it's unsteady. So what has to happen? What has to happen in this control volume if for it not to be steady state?
The mass flow has to be different.
Right. That's a good example. This has to be gaining mass. If the mass flow in and out is different, there has to be a mass accumulation within this. So the pressure in here is constantly increasing. What else would have to happen for it to be unsteady? What another example? The counter is kind of hard to think of sometimes, but let's come up with something. Let's come up with some. So mass was a good one. Mass balance, to do mass conservation, right? Is a good way to double check to think about if something's steady state or not.
The energy changes.
Okay, so that's the most basic one is energy, right? So what has to happen to the energy within here?
Goes up or down.
It has to be changing, right? But we've already identified that our mass coming in, the rate of mass leaving and the rate of mass entering are constant, right? So that would mean that we'd have to have some changing temperature of the mass leaving. This would not be constant over here, or it wouldn't be over here. So in that case, we would need to be putting some an extra chiller right here or something like that. We'd be putting an ice cube or something, taking it off. Or we'd do it on this side. I don't know. We would have to have some way of changing the energy within here. So we'd have to be changing the rates of the internal energy of that coming in or the internal energy of that leaving. Nevertheless, our system is oil and it is operating at steady state. So if we do a full energy balance, we got m dot H1 plus m dot dgz1 plus m dot this is for the oil coming in minus m dot H2 plus m dot Z2 plus m dot. Of course, I've already put subscripts, but I'll just be redundant. And so I have in here, so I have work in plus heat in. And on this side, I have to have minus work out minus Q out equals 0. So we've already discussed that in problems like this, there is no work transfer. This boundary isn't changing. The size, right? The surface area of my boundary or the volume within my boundary isn't changing. So there's no boundary work. I don't have electric wires coming in where there's power crossing it. Some other form of energy, right? Which can be looked at as power. Do I have heat in to here? Is there heat input to my oil?
No.
So this is 0. How about heat out?
Yes.
So I do have some heat out. Now of course there is some Z2, right? But Z1 equals Z2. So So I can get rid of these. Now I do have a temperature and pressure of the input relative to the output, so H1 does not equal H2. Now, in terms of velocity, how does the velocity of my oil entering my control volume of oil compare to the velocity of the oil leaving my control volume? Okay, so these are basically the same two. So basically it all just simples down to I got Q dot out is equal to M dot H1 minus H2. And then if I can approximate like that as M dot CP average T1 minus T2 if I want. So for this term here, I can use tables, right? And this one here, I can also look up value or use tables. And remember that this is the specific heat at constant pressure. So I already wrote this. So just write M dot CP average T1 minus T2.
Let me look that up.
So now I want to go back to this idea of specific heat and the rate of heat transfer. So I did energy balance to solve an expression for this control volume. Now if you recall from freshman physics, the heat associated with phase change is equal to the amount of mass for a given phase change process times delta T. So if I want to know, so this is freshman physics. And we basically did the same thing here, but now we have dots, but of course I can do this, so I have some M dot CP. And here I have a delta rate, so I can just do Q dot equals M dot CP delta T. So I use this in this formalism to get me this expression. Here I went from freshman physics and just kind of put it in rate form. So partial H, partial T at constant pressure. This is, what do I have to do to fill in the heat capacity at constant volume? What is this? What's that? U at constant volume. So one's the partial of internal energy and one's the partial of enthalpy. So partial U with respect to T at constant volume is the heat capacity at constant volume. Partial H with respect to temperature at constant pressure is the heat capacity at constant pressure. So if you ever need to know the enthalpy and it's not tabulated, if you need to know the enthalpy and it's not tabulated, what should you look for? Just write it based off this expression right here. You need to know the enthalpy and you can't find it. What should you look for? Someone asks you, what is the enthalpy of this refrigerant at room temperature? Or no, they ask you, what is the enthalpy of olive oil at room temperature? That's what they ask you. They need it for some cooking experiment. I don't know. Right? So what should you look up? You can't find it. You Google everywhere, you can't find the enthalpy.
The specific heat.
Yeah, so then you do a Google search on the specific heat, right? And you can always rewrite this, and remember this is a derivative, so you can, right, integrate both sides. And now you got the change in enthalpy related to the, and so now if you have the specific heat at a couple temperatures, you can calculate H. You'll probably do something similar to that with something you're dealing with as an engineer later on. If you deal with heat transfer type things. This won't be tabulated, so you'll just look up what somebody measured for this at a couple different temperatures, and then you'll use this, and then you use this delta H to predict the change in entropy, which we'll get to later on. Okay, so I did energy balance on the oil. The next thing to do is to do energy balance on the water. So the same thing happens. So I do energy balance on my control volume of water. So I have the rate of heat in plus the rate of work in plus m dot H2O. And I already know the velocities and stuff, but I'll put them in. Minus equals 0. Then I can cross these out. I already know the velocity of my water coming in is the same as it's leaving. There's a mass flow rate, so I can get rid of this term. My reference, really the water went the other way, but so my references can get rid of, but of course my water left, I'm using water to cool my oil, right? So my water leaves at lower temperatures, so H1 is not equal to H2. And in this case, I don't have heat leaving my water. But I have heat entering, and I have there's no work out, there's no work in. So I do that, and I just get Q dot in H2O is equal to m dot H2O H2 minus H1. And of course, now I want to look at, so Q dot out water is equal to Q dot minus Q dot so I can put a minus sign there. M dot H2O H2 minus H1. And this term here, I can rewrite that in terms of m dot H2O CP average H2O T2 minus T1. So in this segment up here that I skipped, it's just from the perspectives of oil. So heat loss by oil is heat gain by water. So Q dot oil out equals Q dot Well, if I right here, I put a minus sign. So we had it from the perspective of out for oil, and when I put it in the perspective of out for water, it's the same thing.
Oh, okay, so like.
So really, it's not out for water; it's in for water.
Okay.